So in my time here, I've been in Alaska now for 7 winters. I've taken the winter time to explore the landscape here in Alaska, and that's a time when glaciers are covered with snow. We can't really see them, and they're not really accessible for us to study because they go into a quieter state in the wintertime. I'm a professor of geophysics. My specialty is glaciology, so I study ice in glaciers and ice sheets all over the world. So in Alaska, in Antarctica, in Greenland, in the Washington and British Columbia area. So I mostly study land ice, how it flows, and how it responds to climate change.
And science. My name is Caroline. I'm on exchange here at UAF from McGill University back in Quebec. And I came to UAF to study glaciology and learn about ice. And I guess Alaska is the perfect spot to do it because there's so many glaciers everywhere.
It's lovely out here, isn't it? I got really intrigued by the way waterfall ice, the waterfalls that freeze and evolve over a season and then melt out at the end, they go through this amazing evolution every season that's a much faster change than glacier ice does. And you can then see it over multiple winters and kind of watch how the climate and the atmosphere, the snowfall, the temperatures that we experience during the winter, the waterfall also experiences it. So what I decided to do was get a group of students to go down and do a pretty intensive study of this waterfall over the course of a winter.
My name is David, and in the Dragonfly Falls project I am doing the still camera. This is my box setup, and it is projected to take pictures every 30 minutes, pending weather.
So we're studying it by watching how big it grows. So we have a time-lapse camera that's allowing it to taking pictures of it every half an hour through the whole season to try to get a picture of how the waterfall grows and then melts away at the end. And then we're also drilling in and actually measuring temperatures within the waterfall ice.
Minus 7.7. 7 point... It's freaking out. I work with Aaron Pettit on the waterfall ice, and my job is to transform the ice cores that we get down at the waterfall into thin sections, which are about 1 millimeter thick sections of ice, and then you look at them in polarized lenses, and then you get to see the crystals. Okay, now is the time to melt it. I just dropped it, and it broke.
Oh my god! Are you serious right now? No!
It's fine. I'm just gonna glue it back together or something. Right now, so basically this is still, the ice is too thick to see the crystals, but in the end what we want to do is we want to try to compare how the ice looks like at the crystal level when it's very, very thin and we can totally see the orientation of the crystal and the size, and how it looks at a more macro scale when it's big and you can see the layers and you can see the air bubbles. So the relationship between the two is quite fascinating, I think. So I have to take pictures now of what it looks like when it's the normal ice, when it's thick and all white and with bubbles, and then I'm gonna be able to, using a computer, make figures of this one next to the one I have with the polarizing lenses, and that should be very awesome.
So we have colleagues in France, Maureen and Jerome, and I've known Maureen for a number of years because she and I both have a fascination and spend time studying the actual micro crystals within a glacier or within an ice sheet. So we zoom in on the really small scale of what the ice really looks like deep down. And so she and I have developed a collaboration on some of our Antarctic projects. And then through time, she started telling me about her starting to study waterfalls in the Alps. And a few years ago, she got some funding through the Petzl Foundation to study waterfalls in the Alps. And so she's been pursuing that, and because we have this similar interest in the structure of ice crystals, she and I got quite interested in sharing some of those ideas, and she became interested in wanting to know what was going on in Alaskan waterfalls. And so this winter we were able to have them come visit and show them what our waterfalls look like. And it turns out, after talking about that, the icicle formation, this initial, what we get early season, which are lots of icicles forming, that's mostly what they have all season long. So they have a lot more icicles coming down, and there's a lot more holes and gaps of air within the waterfall ice in the Alps. Whereas ours, when it gets deeper into the winter, the water fills in those air pockets with solid ice. So the waterfall ice here is much more dense. I think in general, our waterfalls are a little bit sturdier in some regards. But that depends a little bit on the source of water and a little bit on the temperature over the course of the winter, how it's going to evolve. We're also studying the temperature of the waterfall, because it's the temperature that really determines how much it's going to grow and how quickly it will shrink. It will melt in the spring. And we're doing that using both a thermal infrared imaging camera, which allows us to see temperatures in the waterfall that are features we can't see with our naked eye. What this has taught us, a really neat thing that it's taught us, is basically early in the season, waterfalls grow by the formation of lots of icicles, and you'll see icicles might grow off the side of a building or off of a rock or anywhere that there's water available. But in this case, they grow into these big icicles, and the icicles get bigger and bigger, and then at some point it shifts, the water backs off and the temperatures get a little bit colder, and then the water, instead of making the icicles longer, the water freezes before it gets to the tip of the waterfall, so it makes the icicles fatter. And as these icicles get fatter, they merge to each other and become this massive form. And then after that, there's basically, the waterfall grows by having a thin film of water flow down and thicken it slowly through time. It's been a neat evolution to understand structurally in terms of how the temperature changes, in terms of how the crystals grow, and we can view this with the thermal camera, because when water freezes, when it turns from water into ice, it actually releases heat on that process. And that heat that releases when the water freezes actually warms up the surrounding ice. And so even on a day where it's -40, for example, we can see ice that's at -40 because it's been there for a while. But where it's newly freezing ice, you can actually have waterfall ice that's at as warm as 0 degrees Celsius, so very close to the melting temperature. And you'll see a stripe, in the thermal images, you'll see a stripe of really bright red ice that's that warm ice, right next to really cold ice that'll be dark purple or black in our thermal images. And this contrast is just it's a really interesting process to see it happen in real time. And this is the kind of process where you have strong temperature gradients with flowing water that persists throughout the winter despite these cold temperatures. That's the kind of process that there's elements of that are happening underneath glaciers, and down in Antarctica within the coldest glaciers we have this water movement even though the temperature of the ice might be really cold. So we're taking what we learn here about the waterfall ice evolution, and we're going to be applying this knowledge to studying some of these subglacial conduits in the water movement underneath glaciers and through glaciers down in the Antarctic. So that's the short version of this particular project.
Yeah, it's very cold.